Hi everyone, Assalamu alaikum. Welcome back to another video on robotics and algorithm. In this video, I will show you my implementation of a map-free reactive motion planning algorithm known as bug algorithm. It's a well-known method used for basic autonomous robot navigation. There are three versions of the bug algorithm, each with its own strength and weaknesses. I will explain and compare all three in this video. So, without further ado, let's jump into it. Let's start with the bug zero algorithm. But before diving into the algorithm, let's understand the problem it aims to solve. Imagine we have a simulated world. I'm using the Gazebo physics simulator to mimic the real world. In this world, our robot starts at a certain position, say at coordinate 0, 0. And our goal is for the robot to reach a target position, such as 8, 2. However, the robot must navigate autonomously. Once it starts, we cannot control it. If there were no obstacles, this would be simple. But in reality, obstacles are everywhere. That's where the bug algorithm comes in. It helps the robot to reach the destination safely even when the obstacle in the way. What does a robot need to run this algorithm? Only two things. A way to move, this could be a wheel, legs, or anything similar. A way to sense obstacles, such as an ultrasonic sensor, an IR sensor, LiDAR, or even a simple wire antenna. In our case, we are using a robot called TurtleBot, which has a LiDAR sensor mounted on top. It helps the robot see what's ahead. Enough theory. Let's see it in action. Here is our robot in the Gazebo simulator. This point here is our destination. I am using ROS to handle consistent messaging between components. ROS also provide a great visualization tool called Rviz, where we can see lots of useful information. Right now, we are visualizing the robot's LiDAR data in the red points and the path it's following, a line for better understanding the algorithm. As you can see, robot successfully reached the destination. How does bug zero work? Here is the logic in simple steps. While the robot is not at the goal, move toward the goal. If it hits an obstacle, follow the obstacle until there is a clear path to the goal. That's it. This simple step defines the bug zero algorithm. Let's apply this in our situation. The robot starts moving toward the goal. It hits a wall, or in our case, it detects that it's too close to an obstacle. So it begins to follow the wall using the left turn rule. When it finds a clear path to the goal again, it resumes moving toward it. This cycle continues until the robot reaches the destination. But does bug zero always succeed? Let's consider a tricky scenario. Here is the start and here is the goal. Pause and try to guess what happened. Did you figure it out? There is a loop formed by the obstacles. Let's simply follow the algorithm and see what happened. The robot will start from here and move toward the goal. When it comes at this point, it will face an obstacle. The robot will start to follow the obstacle. And right here, the robot will find a clear path to the goal. It will follow the path and it faces an obstacle again. And it will start to follow the obstacle. Following the obstacle, it will end up being in the hitting place of the obstacle. So it creates a loop. And our poor little robot will navigate the loop until the battery dies or something terrible happens to him. So, bug zero is not a complete algorithm. It does not guarantee reaching the goal. even if a path exists. Enter bug 1. Let's run bug 1 on the same setup. As you can see, the robot is now takes a completely different path. Let's look under the hood to understand why. Steps of the bug 1 algorithm. While we are not at the goal, move toward the goal. If an obstacle is hit, circumnavigate the entire obstacle. While doing so, record the point where the distance to the goal is minimum, or store that point where the distance to the goal is minimum. Return to the point where the obstacle was first hit. Then navigate to the point with the minimum distance and leave the obstacle there. Let us analyze how it is applying in our scenario. It starts moving toward the goal. Here, it hits an obstacle and start to circumnavigate the obstacle and keep store of the point that give the minimum distance to the goal. As you can see in the terminal, I am printing the current minimum distance, and it is getting updated as the robot find a new minimum distance. So it moves all around the obstacle and comes back to the hitting point. Now it goes back to that minimum distance point. Here it is in the minimum distance point. From here it starts to go toward the goal and continues the algorithm until the goal is reached. This is a complete algorithm, meaning the algorithm is sure to find the path to the goal if it is possible to go to the goal. Let us go back to the previous scenario and see what happens. We start moving toward the goal, hit the wall and start circumnavigating the wall, going around the wall and keeping track of the minimum distance point and return to the hitting point. Now we have a point, maybe here, which is minimum distance point, and the robot will circumnavigate the wall until finding the point. And when it finds the point, it leaves for the goal, and in this case it reaches the goal. So one difference between bug 0 and bug 1 is that bug 0 is an incomplete algorithm, whereas bug 1 is a complete algorithm. Another difference is bug 0 does not need a memory to store any kind of data, but bug 1 needs memory to store the minimum distance point. Lastly, let us move to the bug 2 algorithm. While not at the goal, move toward the goal. If hit an obstacle, circumnavigate the obstacle until finding a point that is on the start goal line and closer to the goal than the hit point. So in this algorithm, we are pre-calculating something, the start goal line. This is the line from the start to the goal, and we are calculating and storing it before running the actual algorithm, and then we simply follow the line. When we face an obstacle, we circumnavigate the obstacle until we are back to the start goal line and we are closer to the goal than the hitting point. Let us analyze in our case. We move toward the goal, following the start goal line. We hit an obstacle here and start to navigate the wall. At this point, we are back to the start goal line, and the point is closer. So we leave the obstacle and continue. As you can see, the bug 2 is generally faster than the bug 1 algorithm. Why? Because bug 1 needs to circumnavigate all around the obstacle, in worst case, twice, but bug 2 doesn't have to do that. But there are some cases where bug 1 is actually faster. But in most cases, bug 2 will outperform bug 1. Bug 2 is also a complete algorithm, meaning it is guaranteed to find the goal if there is a possible path. Bug 1 is actually using an exhaustive search, whereas bug 2 is a greedy algorithm. That's it for this video. Thanks a lot for watching. You can leave a comment, that would mean a lot to me.